Okay, hello everyone. Let's go ahead and take a look at what we're going to do next with regards to linking functions with the power series. And what we're going to say then is that if we have a function and it's going to be equal to the power series expansion, how do we know if they are equal or not? Now, let's go ahead and kind of get a general idea conceptually about what's happening. And then we'll go ahead and take a look at the more nitty-gritty mathematics that's involved in answering this question. Now, as the power series is an infinite series, if we consider only the first n terms, then the rest is the difference from the exact value. Okay, let me go ahead and describe exactly what that's referring to. Now, we've seen before that f of x equals e to the x is equal to this particular power series expansion. Let's go ahead and say, for example, that instead of going all the way to infinity, we only go up to the first four terms with n being equal to 3. So if I was to go ahead and write that expansion from n is equal to 0 to n is equal to 3, I would come out with 1 plus x plus 1 half x squared plus 1/6 x to the third. Now, if I wanted to go ahead and say, for example, find f of 2, which is, of course, e squared, I could go ahead and approximate it to 1 plus 2 plus 1 half times it by 2 squared plus 1/6 times it by 2 to the third. And I know for a fact that e to the second, by using my calculator, is going to come up to something that looks like this. Now, the approximated value is going to be 6.3 repeating, which is a horrible approximation. But the idea, though, is that whatever is the rest is actually the difference between this value and that value. Okay, so that's what we're talking about when we refer to this. If we consider only the first n terms, then the rest, that of course is not considered, is going to be the difference from the exact value and the approximated value. So what we have then essentially is this. I have f of x is going to be equal to a series from n is equal to 0 to some value n, plus whatever is remaining, which is going to be considered the remainder, or the difference between the exact value and the approximation. Now, if I go ahead and take the limit as n approaches infinity of both sides of this particular equation, and I can show that the limit as n approaches infinity of this remainder part, if that goes to 0, then basically what I come up with is f of x is equal to the limit as n approaches infinity of this particular series. Well, if n is going to go to infinity, then, well, we have the power series. So the key then is for us to go ahead and make sure that we can write it in this way, and then go ahead and show that as the limit as n approaches infinity of the remainder goes to 0. If we can do that, then we can show that the power series expansion and the actual function itself are equal. Okay, so we'll go ahead and take a little bit more in-depth look of the nitty-gritties that are going to have to will allow us to show whether or not a power series is equal to a particular function. Okay, see you later, bye. Okay, let's go ahead and take a look at the Taylor and the Maclaurin series. We're going to continue with what we had just saw before with regards to the general concept of what we're trying to do in answering the question when a power series expansion is actually going to be equal to a function. Now, we have two different types of series that's named here. One is the Maclaurin series and the other is the Taylor series. Basically, they are both the same, except for the Maclaurin series is centered at the value a equals 0. The Taylor series, on the other hand, can have a centering value at whatever value you want, so long as it's in the domain of a function. So what we'll say then is that, in the broadest sense, let's take a look at the Taylor series, that f of x is going to be equal to the summation from n is equal to 0 to infinity of c sub n times the quantity x minus a raised to the n power, where c sub n is going to be equal to the nth derivative of f of x divided by n factorial, where all of these pieces are true as well. Well, we know for a fact that 0 factorial is going to be equal to 1. We're going to go ahead and say, being that we're using our series notation, that this will refer to just f of x. And of course, we have a radius of convergence. And if we expand that, we come out with what is called the interval of convergence. Now again, the main question is, when is the Taylor expansion actually going to be equal to f of x? And remember we said that the answer will be if your remainder goes to 0, if you take the limit as n approaches infinity of the rest of the expansion. So what we're going to do then is we're going to define this a little bit more clearly. It says that the nth degree Taylor polynomial approximation to f of x about x equals to a is going to look like this. Now it's nothing different from what we have here, except for the fact that we're only taking the first n terms. And what we're going to do then is we're going to go ahead and use this notation here to talk about the remainder. In other words, everything that's left. Okay, when using the error involved when using t sub n to approximate f of x about x equals a on the interval of convergence is going to be written as such. So notice that if we have f of x is equal to t sub n plus r sub n x centered at a, then what we have is this particular remainder is going to look like this. It's going to look exactly like the next term. And if we go ahead and take a look at that next term, the only thing that's going to be different is that instead of x, notice that x right there, instead of x, we're actually going to have a value of c. Now, what is that value of c? That value of c can be anything that you want to choose from the centering value to any particular value x. Okay? There's also going to be this other integral form of the remainder, and we'll talk about that a little bit more in class. Now, let's go ahead and get back to our original question here. Now that we know how to express the remainder, how do you go about showing whether or not it is actually equal to 0? Now let's go ahead and take a look at a Maclaurin series of f of x equals e to the x centered about x is equal to 0. Now we've seen in the past that this is actually going to be equal to this right here, except for we usually associated the infinity power series for e to the x. But again, remember what we're doing right now is we're only taking a look at the first n terms. So if I go to summation from n is equal to 0 to n of x sub n divided by n factorial, what I'm going to come up with then is another form of e to the x looking like this. T sub n plus r sub n x centered at 0. Now, what I'm going to take a look at then is that r sub n x centered at 0 is going to be equal to this. Now remember, I can choose any value of c, so I'll just go ahead and put it as c because it's going to be a constant. Now what I'm going to do then is I'm going to consider all of those particular remainders all together. And so to a certain degree what I'm doing is I'm actually going to be adding all of them up as a power series, and I'll write it as a power series. So what I have here then is the power series notation for the remainder. And what I'll use then is, being that that's a power series, I'll use the ratio test to determine whether or not that converges. So if I go ahead and use the ratio test, I come out with this, which is obviously equal to 0. If I take the limit as n approaches infinity, that is going to be less than 1. Now, being that that's less than 1, therefore I know that the power series converges for all x. X is an element of R. So it doesn't matter what x is, it's going to converge. Now, if the remainders added up all together are going to converge, then that must mean then that when it comes to the actual sequence, the sequence values actually have to converge as well to 0. And therefore what we can say now is, being that we've shown that this is going to be equal to 0, we can then go ahead and say that f of x is actually going to be equal to e to the x, which is going to be equal to the power series expansion n equals 0 to infinity of x to the n divided by n factorial. And we know that that's going to be true for all values of x. Okay? And so there you go. That's how we can go ahead and show now, given a particular power series expansion of a function, we can go ahead and determine whether or not that function and the power series expansion are actually equal to each other. Okay, so we'll take a look at some of these examples in class and we'll see how we can do. See you then. Bye-bye.